Hello everyone. Uh, in this particular lecture, we'll be studying about how an op-amp can be used as an integrated circuit. It means that your op-amp can also be designed in order to integrate the output voltage with respect to the input voltage. Means what? Uh, your output will be an integral of an input voltage. Your Vout is going to be an integral of a Vin voltage. So that's what we are going to study in this particular lecture. So now let us enter into this one. So here, what is an integrator? Integrator, or else it is also called as an integration amplifier, which performs mathematical operations of integration. It is just like a integration or integrator operator which you use in the mathematics. It does the mathematical operations. So its output voltage waveform is always an integration of an input voltage waveform. The output will be always an integration of what my input voltage. So that's why the integrated is most commonly used in signal wave shaping circuits. So integration is used for the signal wave. What is the example of that one? That is just like analog to digital converter. It is this one of the important objective. Integrated is used for signal wave shaping circuits. Used in the signal wave shaping circuits just like ADC. And it is also used in the analog computers. This is the basic integrated circuit. If you see the basic integrated circuit here, you can see here it is an inverting integrated circuit because my input is been connected, Vin is been connected to the inverting terminal. We can see what is here. We can see for the Vin as input signal, we are having one resistor R1, and that R1 is connected directly to the inverting terminal, and there is another feedback circuit, feedback component. That feedback component is a passive element which is nothing else but the capacitor. Usually we do not see the capacitor in the feedback, but in integrators we see a feedback capacitor. So let the name of the capacitor equal to CF. Why? Because it is a feedback, so I have named it as a CF. And the other terminal of the integrated, that's a non-inverting terminal, is directly grounded. And this is the output Vout, and the RL is nothing else but RL is a load. RL is a load. Now we are supposed to find out how this output Vout is an integration of the input. You can see now your output is an integration of your input Vin. So this thing we are supposed to find out. This is your final output voltage, that's Vout equal to integration of input voltage. So now let us try to derive this output voltage. See now, let us try to apply the expression of output voltage Vout. In order to obtain this expression of output voltage Vout, what you are supposed to do? We should know the KCL over here. See now, your voltage is supplied here, Vin is supplied here. It means the current, some current will be passing through from this one. Let that current equal to I1, and that current is passing through the R1, and it is going to a node V2. So at this node V2, we are supposed to find out the what is that KCL. Why we are supposed to find out the current loss here? Because the current entering into the node is equal to current leaving the nodes. This I is going to become the sum of these two. What is the sum of which two currents? One current is the bias current of this terminal, and other one is the current which is passing through the feedback loop, that is the IF. So therefore I1 is equal to IB plus IF, and we know that what is the IB? IB is nothing else but it's a bias current. Because my op-amp has got very high input impedance, the current cannot go into this input terminals. That's why I'll be considering my IB equal to 0. Your IB equal to 0 means what happens in your equation? I equal to IB plus IF will be your equation as per the KCL. I1 equal to IB plus IF. Why it will be IB plus IF? Because this current is entering the node and these two currents are leaving the nodes. The KCL tells that the current entering the node is equal to current leaving the nodes. So I1 is equal to IB plus IF. Here IB is what? IB equal to 0. Why? Because your op-amp has got very high input impedance and it will not allow the current to pass into these terminals. So that's why IB equal to 0. So ultimately what we will get? We are going to get from the KCL equation at the node V2 I1 equal to IF. I1 equal to IF will be your main first equation in order to calculate this output voltage. So if we apply the Kirchhoff laws at the V2, we are going to get I1 equal to IF. So see now. Writing the Kirchhoff current equation at the node V2, we are going to get I1 equal to IB plus IF. Since my IB is 0, I'll be having I1 equal to IF. And if you substitute over here, you'll be getting the final equation. If you substitute IB into this one, you'll get I1 equal to IF. And this is what? This is the relationship of current through and again a voltage across this particular capacitor. You are trying to find it out, the relationship of current and voltage across this particular capacitor. What is that capacitor? This is a capacitor. Why? Because I can directly write by Ohm's law what is the current passing through the resistor, but I don't know what is the I can't directly write what is the current which is across these two plates of the capacitor. So for that one, we have studied one formula as per the basics of the physics. What is the formula for that one? The current across this capacitor will be I equal to C dV by dt. I equal to C dV by dt. What is VC here? VC is the voltage across this one. VC is the voltage across these two plates of the capacitor. So it is VC. That C indicates it's a capacitor. So it is IC equal to the current and the voltage across this one is being represented as C. Suffix C means it is across this capacitor. So I equal to C dV by dt is my basic formula. Now I need to apply this formula in this equation I1 equal to IF. When I apply this formula, I'll be getting, see, when you apply this formula, you're supposed to change the suffix C. Why? Because my feedback resistor here, my feedback current equal to IF and my feedback capacitor is CF. So it will be in terms of F for the next calculation. So see now. Therefore, what I'm doing here, I'm trying to write this I1. I1 I'm trying to write in terms of Ohm's law, and again this one IF also in terms of this equation. IF will be in terms of this equation. Then what is I1? Let us go and see what is I1 here. What is I1 here? How to find out the I1? I should have the Ohm's law equation, that is V upon R. So now I1 equal to what? There are two voltages. This I1 is traveling from V1, sorry, it's traveling from V in and it is going to the V2. So it means what? V in is much greater than V2. So therefore, the potential difference between these two will be between V in and V2 will be V in minus V2. So my I1 becomes V in minus V2 upon R1. V in minus V2 upon R1. The same thing we have written here. See, it is V in minus V2 upon R1 equal to what I told just now. I need to write this IF equation in terms of this one, the current and voltage across the capacitor. This one I need to write. So it becomes as what? CF, and you should find out what is the potential difference at the two terminals of the capacitor. If you know that one, then you can substitute the value of potential here, and this C becomes CF, and that potential you should substitute and you should write it that formula. See now, it becomes CF into d by dt, and what is V here? V I should write the potential I told. So how to calculate the potential? You can see here now. The IF is traveling from V2 to V0. IF is traveling from V2 to V0 means what? V2 is greater than V0. So the direction of this current tells that which voltage is which potential is greater. So V2 is greater than V0. So you should take it as V2 minus V0. So here in the formula of this formula, in place of V, I should write it as what? V2 minus V0. You can see here now. CF into d by dt, it is V2 minus V0. So now we have converted our I1 equal to IF into this equation. And what about the V? We are having the V2 here. Why? Because I don't have exactly what is the value of V2 in my circuit. I don't have exactly what is the value of V2. But if I assume this as my V1, then this becomes my V2. Here this becomes my V2. If I assume this is my V1 and this becomes my V2. Now I'll try to apply the virtual ground concept. What is the virtual ground concept? Because these two terminals are internally connected or internally shorted, because of that one, the voltage across this one is going to become 0. That's why the V1 is going to become 0. That's what we call it as that's why we call it as an virtual ground concept. It is called as what, ma'am? Virtual ground concept. So virtual ground concept means what? Internally these two terminals are connected or shorted. Because of that one, the voltage over here will be 0. That if V1 is equal to 0, this voltage is also 0. Why? Because they are connect directly shorted. So if this is V 0 means this also is going to become, this terminal voltage also becomes 0. That is directly connected to where? To the V2. So therefore V1 is equal to V2. Therefore, I'll get, since V1 equal to V1 equal to 0 volts and V1 equal to V2 is also 0 volts. That is by the concept of virtual ground. Now you substitute V2 equal to 0 here in this particular equation. If you substitute, what you are going to get here, V2 is equal to 0 and V2 equal to 0 in both these sides. You are going to get, after substitution, Vn by R1 is equal to Cf d by dt that is equal to minus V naught. If you apply the integration on both the sides, you will be getting this equation. You will be getting this both the equations. Class Luna. Class Luna petty. Now let us apply this integration on both the sides. If you apply the integrations on both the sides, what happens here with respect to time? This is we are integration of 0 to t v in by r1 dt, that is equal to, apply the integration also on this side. If you apply the integration, you are going to get this equation, that is Cf into minus V naught plus V naught and whenever the time equal to 0. And ultimately you are going to find out what is the value of V naught. What's the value of V naught here? V naught equal to 1 by R1 CF. 1 by R1 CF. Do some mathematical simplification on LHS and RHS. Your equation will be converted into this type. V naught equal to minus 1 by R1 CF integration of 0 to t V in dt plus constant. So ultimately we have got the equation that which tells that your output voltage is an integration of the input voltage. Your output voltage is an integration of the input voltage. So now the circuit which we are talking here, this circuit is acting as an integrator. What it is doing? It is integrating the input voltage and giving some output voltage. It is integrating the input voltage and giving the output voltage. So that's why we call it as an integrated. This is a equation which you have found out there. That's V out equal to integration of V in. See now, this is your final equation which you have found out. What is where C is the integration time constant and it is a proportional to the value of V naught at time t equal to 0. This is C is the integration time constant, but what is that? It is proportional to V naught whenever it is time t equal to 0. Thus, we can say that from this equation, the output voltage V naught is directly proportional to the negative integral. We are having negative sign, right? Output voltage is directly proportional to negative integral of what? Input voltage, and inversely proportional to the time constant R1 and CF. So this is your final what is meant by integrator and how your integrator will be working. Now let us see, whatever we have talked up to now is regarding ideal integrator. Now let us go to the practical integrator. What happens in the practical integrator? We will try to see why we are using the practical integrator and what is the use of using that practical integrator. We will try to see now in the next slide. The next slide talks about what is a practical integrator and why we are supposed to use that practical integrator. So see now, in the practical integrator, we are using two resistors, two passive elements. This is the one passive element R1 and the other passive element you can see here RF. So this R1 and RF is the two passive elements which we are using over here. Why do we use this passive elements R1 and RF here? Because this particular circuit will be undergoing some kind of low frequency roll-off problems. In the low frequency, it will be having some noise problems or roll-off problems. Rolling off, you know, what is the rolling off? We have seen in the different op-amp circuits. So that kind of rolling off problems will be there in your ideal integrated circuits. In order to overcome that rolling off problems, and also there will be some, if there is a rolling off problem every time, then definitely what happens, the stability is not going to be good. So in order to overcome this stability problem and rolling off problem, we are going to have this additional resistor RF and also the R1. These both are connected in order to overcome that particular rolling off problems. So these two are the extra components which you are connected to the ideal integrator. So now let us see this one. So these are the waveforms which talks about this particular integrated circuit. So let us see what does this waveforms talks here. So here, if you see this waveforms, in this waveforms, in this waveform, what is there? If the input is sine wave, the output is going to be ultimately cosine wave, depending upon this what are the integration we have done. Or else, if the input is square wave, the output is going to be the triangular wave. This is what we have seen here. If the input is sine wave, your output is going to be a cosine wave. Or else, if you are giving a input as a square wave, the output is going to be the triangular wave. But what is happening there? Since we are having in our formula, if you see the formula is having what? Minus sign. Because of this minus, we are getting this one. It's an connected to the input is connected to the inverting terminal. So that's why if you are giving an sine square wave input, you are going to get a triangular inverted triangular wave. And again, if you are giving a sine wave, you are going to get a cosine wave over here. So that is regarding this waveforms. So now here, if you see this one, these waveforms are drawn with the assumptions that R1 and CF is equal to the product of this one. These waveforms are drawn that with the product of this one, R1 and CF is equal to 1. Whenever this complete term is equal to 1, it is direct integration of V in. So it acts as a direct integration of V in. Therefore, my out is going to be 0 volts. But that is, your capacitor is completely C is going to be 0. This is going to be 0. Now let us assume what happens why we are supposed to use this RF also. We have seen your RF is what I have told. This RF is acting in order to avoid the roll of conditions. It means what? This RF will limit the low frequency gain, and hence it will minimize the variations in the output. That is an important term. See, this is all. How can the designers know about this RF? Whenever they do some kind of research, and when while doing the research, they'll connect this RF, and they'll see how this RF is acting upon this particular integrator. Then they have found out that whenever this RF is connected, this RF is trying to limit that low frequency gain, and it is also because of that one, it is minimizing the variation of the output voltage. So that's why this RF is connected as a feedback resistor across this CF. That's the main important terms regarding RF and C1. And this is the input output waveforms. And let us now see what is this frequency response. See, this is a frequency response which tells about relationship between the ideal and practical integrators. In the frequency response of an integrator, you can see that in this figure, IB is what? IB is a frequency. You can see now. What is this IB? IB is a frequency at which the gain is going to become 0. IB is a frequency at which the gain is going to become 0, and we'll try to see in the next slide what is the formula for the IB. So IB is a frequency at which gain is going to become 0, and you can see this is the actual, this one as per the integration. If you apply the each and every value of the input voltage, the output voltage, you can see with respect to that output voltage, this is a gain which is obtained. So it is a basic integrated response, and this one you can see it is just this curve. This curve is the ideal response of a practical integrator. And for this one, what is the relationship between RF upon R1? The relationship between RF upon R1 is nothing else but the slope. That is nothing else but your 3 dB. It's a minus 3 dB slope. This is a minus 3 dB slope. And this, wherever this minus 3 dB slope takes place, we call it as what? It is a it's a corner frequency, or else it is a cutoff frequency. So now this is nothing else but it's a 3 dB gain. So this is the frequency response of your basic integrated integrator and also the ideal integrator. See now, this is the formula for FB. What I told, FB is what? FB is nothing else but it's a frequency where your gain is going to become 0. So that formula we have written in terms of that frequency formula we have written here. That is equal to 1 by 2 pi R1 into CF. This earlier we have talked about this one. R1 and CF are the most important parameters which are going to vary the output. So we have written FB equal to 1 by 2 pi R1 into CF. And now let us see how the proper integrator can work. Now here, whenever the time is equal to greater than or equal to RF into CF, if time is greater than the product of these two, then we can write down the formula of this one. RF into CF equal to 1 by 2 pi into FA. And if you substitute this value of F here, earlier we have seen, so ultimately you will get FA equal to 1 by 2 pi RF into CF. It's a cross multiplication we have done. So we have got the formula for this FA. FA formula is now derived here, that is equal to 1 by 2 pi RF into CF. So this is how we are supposed to find it out. What is the minus 3 dB gain frequency and what is the frequency at this FB. So these two formulas have been given. Even if you do not know how to find out with the help of this graph, since you know the values of R1 and CF, because you are the main designer who is designing this integrator, if you know the value of R1 and CF, you can find out what is the FB, what is going to be the frequency, where that gain is going to become 0. And if you know the formula, if you know the value of RF and CF, you can find out where that minus 3 dB gain is going to happen. So this is regarding what is meant by what is meant by integrator, and these are the references which I have taken from Ramakant Gaikwad book.